Good morning, everyone, and welcome to the second edition of MathXplore, organized by the Engineering Mathematics Society of University of Peradeniya. I am Atulya Ratnayaka, and I am delighted to be your host for today's session. MathXplore is an initiative aimed at bringing together experts and enthusiasts in mathematics to explore exciting applications and breakthroughs in the field. Today, we are honored to have with us a distinguished speaker who has made significant contributions to applied mathematics and dynamical systems. It is my pleasure to introduce our speaker, Professor Bernd Krauskopf, a leading expert in dynamical systems. He is a professor at the Faculty of Science, Mathematics at the University of Auckland, New Zealand. His research spans a wide range of topics, including bifurcations of vector fields and maps, computational methods for dynamical systems, systems with delays, nonlinear dynamics of lasers, and aircraft ground dynamics. Professor Krauskopf has made substantial contributions to applied mathematics, particularly in dynamic systems in applications, and he actively supervises PhD students in this field. His work has significant real-world implications, including the topic of today's talk, keeping aircraft on track, the mathematics of high-speed ground maneuvers. With that, let's warmly welcome Professor Krauskopf as he takes us through this fascinating topic. Professor, the floor is yours.
Thank you very much for the invitation and for this very kind introduction, and everybody for showing up on a Saturday morning. So indeed, my talk is called Keeping Aircraft on Track, the Mathematics of High-Speed Ground Maneuvers. And this has been some work that I've done in collaboration with Mark Lowenberg at the University of Bristol and colleagues James Rankin and Mathieu de Roche, who are now in France, and Sanjeev Sharma and Etienne Katsev at Airbus. So this was a joint collaboration over several years with Airbus while I was in Bristol. So let me get going. You can see a picture of an aircraft at the bottom left, and this is probably how you see aircraft as flying machines, and that's of course correct. But aircraft also need to maneuver on the ground. Hang on, okay. And this is the motivation for today's talk. So in fact, in the air, aircraft are all pretty much flying at the same speed. I'm talking about commercial jetliners. And really the money that you can earn is by quick turnaround on the ground. You may have heard of low-cost carriers, and the whole idea is to have the aircraft on the ground as little as possible and just be flying all the time. So that means that you have to safely and comfortably for the passengers be able to drive the aircraft as a ground vehicle. And that is driven by, as I mentioned, turnaround time. But the other thing is also automation. You may be interested to hear that the only time that you can be sure that the pilot is actually actively operating your aircraft is when you are on the ground, because most actual flight operations have been automated. But driving an aircraft on the ground is a lot harder in some sense. And you can see the picture on the left. This is an example where the aircraft left a taxiway and got stuck in the grass. This is not a bad accident in that sense that nobody got injured or so forth, but it's a very expensive hobby to put aircraft in the grass because it costs a lot of money to get them out of there, and you have the restricted operations at the airport and so forth. So the basic challenges for aircraft ground dynamics is how can you ensure the stability at high speeds of takeoff and landing. So basically nothing should rattle loose or be uncomfortable when you take off or land at very high speeds. That's not something I'll be talking about today. But the other question is, how can one move the aircraft as fast as possible between runway and gate? And of course, always subject to safety conditions and passenger comfort and so forth. Okay, so this is the second question we'll be talking about today. Now, to start off with, the landing gear of an aircraft is actually a very nonlinear system. So handling aircraft on the ground is very nonlinear. What do I mean by nonlinear? I mean that if you change some parameter, the reaction of the system is not merely linear. It could be stronger or weaker or whatever. And the reason for this is that you have so-called oleos. These are the shock dampers. They are highly nonlinear. And of course, you have damping, compression, you have friction, you have saturation. You cannot damp any load. Then the tires themselves are also really very nonlinear things. If tire dynamics is a complicated field on its own. And then you have aerodynamics, and you may know this famous formula, 1/2 rho v square. So the aerodynamics goes up with the square of the velocity. So when you go very slowly, that doesn't really play a role. But if you have just landed, there's actually considerable load because of the tail plane of the aircraft, right? So if you want to turn and you have a tail plane, that tail plane will actively basically object to the aircraft being turned if you're very fast. Okay, so this is a very nonlinear problem, and that's why we approach it with nonlinear methods. So let's have a look. The question is, how can we move an airplane as fast as possible between runway and gate? And I'm concentrating today on high-speed turning maneuvers. What is this? You land at the runway, and probably you've all flown, and then the aircraft has to turn off, and there are different kinds of turns. There are basically different angles of turning. It could be up to 90 degrees or even 135 degrees, and you want to get off the runway as quickly as possible at still reasonably large speeds. First of all, to evacuate the runway to allow the next plane to use it. And secondly, because you want to use that speed that you already have to get to the gate as quickly as you can. So when we're talking about high-speed turning maneuvers, there's a number of specific questions we can ask. When is a turn stable? That's obviously really important because when you come off, you don't want to miss an exit or go too fast. I know if you're driving cars, motorcycles, or other vehicles, you know that one shouldn't go too fast around corners. And what does that mean for an aircraft? And then the other interesting question is, how can a turn actually become unstable? So this is really the question, what are the stability boundaries of high-speed turning maneuvers? This is, of course, an interesting question. From the applications point of view, you need to know where are the stability boundaries. And I'll be showing you some, and we have some techniques to calculate these boundaries directly. And of course, the real fun part is what are the possible dynamics of the aircraft on the ground, including when the turn is no longer stable. Now, this is, of course, mostly of mathematical and academic interest, and airlines and aircraft manufacturers are, of course, very keen to avoid this kind of dynamics. They just want to turn as fast as they can, but stably, and get off the runway. I would be very keen for people to have questions at the end of my talk. But to begin with, I have a question for you. Okay, what is funny about an aircraft as a ground vehicle? I'm not sure how practical it is over Zoom to have people, but you ask questions or try to answer this question. But if you are brave, you can type in chat and tell me what's probably funny about an aircraft. And I have an aircraft right here. I hope you can see this aircraft. It actually says fun plane, and so this is already funny. This kind of plane. It looks slightly different from normal planes, but it has an important property. I don't know, is anybody brave enough to give me an attempt at answering this question, or you can also speak up on Zoom? Oh, there's a chat. Excellent. Let's see. The wings. That's, of course, excellent. Yes. You wouldn't build a car with wings. Fuel efficient. No reverse gear. That's also very, very good. Anything else? No traction on the wheels. That's also excellent. Right. So, I mean, aircraft are really not like cars, right? Aircraft are supposed to fly. Yes, they have very small wheels. Okay, this is fantastic. I like people getting engaged here. The key thing, though, that I would like to get to, nobody's yet come up with, and that's not a criticism at all, but let's see. Okay, so actually aircraft, normal aircraft, the smaller types at least, they have a tricycle configuration, right? They have a nose landing gear and they have 2 gears under the wings. Of course, much bigger airplanes have even more wheels, and we studied that too, but the classical mid-sized passenger aircraft has 3 wheels. And I don't know, you probably had this kind of toy when you were younger, or maybe you're still driving around on a trike. And then therefore you know that if you go around the corner, you have to be really careful because this could be very tipsy. I mean, if you go with this too fast, you will basically topple over. And so the key thing is that we have a tricycle configuration of the wheels. You have the steering only at the front. That's not so dissimilar for a car. But because of that tricycle configuration, you somehow feel that the whole thing is inherently less stable. Okay, so far so good. Right, so now, how do you study this kind of a system? Well, I mean, we work with Airbus, so they have industry-developed models. This particular model I'm showing you is done under sim mechanics, which is, you may have heard of it. This is under MATLAB, and it's a way to have multi-body systems and so forth. So let's talk about this model a little bit. So in the middle here, I hope you can see my mouse. You have the airframe. So this is basically a rigid body dynamics. And then you have to add everything. So you have to add the thrust of the engines. And so the comment we had earlier was absolutely right. The wheels are not driven. You have thrust from engines, typically under the wings, but they could be in other places. Then you have the aerodynamics. This is absolutely true. You have the wings, but you also have the tail plane, which is in some sense more important when we want to turn at high speed. So this thing is a 6 degree of freedom thing. You have the ground, you have some aero, all kinds of things. You have displays, body states, and so on. And then you have the landing gear. It's down here. You have a nose landing gear and 2 landing gears under the wings, and they are also modeled. So this is just a very schematic model. So if you would click on any of these boxes here, then you have to specify exactly what is the landing gear really doing, what are the stiffnesses, what are the properties of these shock dampers, how do we model the tires, and so forth. But you get an idea. You basically have the aircraft body. You have to include the aerodynamics, the thrust, and the landing gear. And that gives you basically some sort of black box model, which is quite big and complicated and has been developed, in this case, by the aircraft manufacturer. And this has been developed over quite some time, and it models some specific aircraft. Okay, let's say A320 family. So this models a particular aircraft, and then you have this model, and then you can have a look how the aircraft behaves under certain speeds when you make a turn. Okay, and what we have done is we took some model, this model, which is a sim mechanics model, and we couple it to a software called Auto, and this allows you to track solutions directly and also detect their stability changes and then even track stability changes. I will not go into very much detail about this kind of software, but I will show you some examples what can be done. Okay, so now you have this model, and so what are we going to do with it? So here is what we call a one-parameter bifurcation diagram. So let me talk you through this. So V is the overall speed of the aircraft. So that's the modulus of V. V is a vector, as you know, speed is a vector. And then we have delta down here, that's the steering angle. So the steering angle is really the angle you can steer with. It's like in a car or motorcycle, you have a steering angle. If it's 20 degrees, you're assuming you're making some circle that corresponds to the steering wheel being rotated by 20 degrees. And here's a picture. So what are we plotting here? We're plotting the solution of steering. So we're starting at 70 meters per second, which is pretty large. And when the curve is black, or rather non-dashed, then this is stable. Okay, so this curve means that you start at 70 meters per second, you turn the steering angle just a little bit, just a few degrees, 2-3 degrees. Yeah, you just start steering a little bit. And actually, you're not actually doing very much. That's a very low steering angle, so you're almost going still straight. But what you can see is that the velocity goes down quite dramatically. So that it means, so I should also mention that this is under constant thrust settings. So if you were to go on a straight line, you would keep going at 70 meters per second. So the first lesson from this graph is that if you are steering just a little bit with the airplane, you're not really going around the corner, but you're basically braking the airplane quite a lot. until it is maybe around 35 meters per second, 30 meters per second. This is this point B, and this gives you this circle, okay? So this means that it's a stable turn. You can see if you just hold the steering at this angle, which is about, I don't know, 4 degrees, and you just hold it like this, you will be going around a big circle all the time. Now, of course, that's not what you want to do when you exit a runway, because you don't have that kind of space. But conceptually, would be the stable turn. On the other hand, if you have a steering angle of 15 degrees down here, you make a much smaller turning circle. Okay, you can see this first turning circle has a diameter of about 500 meters. So that means that you're basically not really steering. I mean, you're steering, but you're not really turning. This is a very big circle. And realistic turning circles you only get when you are much slower, as you can see here, around 15 meters per second. Okay, so there's a very rapid transition. You basically, when you start steering, you're basically just braking the aircraft, and only when you're reasonably slow, then you make normal turns. So in other words, it's not a good idea to go at 70 meters per second and start steering, because you'll only be braking. So of course, aircraft generally try to brake with their brakes and go to slower speeds before they make stable turns that are reasonably small. So this has maybe a diameter of something like 75 meters or so, or maybe it's 100 meters, maybe about 100 meters. So maybe this is already appropriate to turn off the runway, depending on the angle that you have to take. Okay, so far so good. Now, of course, there are these two funny points here, H1 and H2, and I'll get back to this later, and this dashed curve. So basically, in this particular area, the turning circle is actually not stable and something more complicated happens, and I will be explaining this later. So from what I just said, you probably suspect that one should go around the corner much slower. You shouldn't start steering at 70 meters per second. But of course, as mathematicians, you can ask yourself what happens if you go even faster. So let's go at 90 meters per second, okay, and start turning. And you can see you're still braking, so the aircraft gets smaller. It starts turning a little bit, but then this picture is much more complicated. This point H2 and so forth. So this region where the turn is not stable is much, much larger. It's this entire area, and here something else happens, which I will concentrate on. So if you were to steer at around this speed, where this arrow B is, you would basically lose the stability here, and you would fall into this area where you have something quite more complicated, which I'll be talking about. And this basically is no longer stable steering, and I will show you what it looks like when an aircraft is no longer steering stably while the thrust level is constant. Now, here's a really interesting thing too, because you can see there's another curve here. There's actually a stable turn over here. Okay, what does that mean? I mean, if I'm over here, I'm steering at 90 degrees. Okay, 90 degrees. And I can actually, I can steer here. And of course, 90 degrees, and I start steering, and then I have another instability here. But there's a stable branch over here of steering angles above 60 degrees and up to 90 degrees, where the turn is stable in the mathematical sense. And that's a really interesting one. And I would like to show you a video that this actually happened in real life. I mean, it's not us who have... we weren't involved in the analysis of this particular incident, but I would like to show you a video. Let me see, I have to do this. Yep. Okay, this is a video of a landing of an A320 by JetBlue. This is 12 years ago. And if you look at this picture, I hope everybody can see it. It turned out that the nose landing gear was stuck at 90 degrees. Okay, of course, it is supposed to point in the direction of travel like the other wheels, but it was actually stuck at 90 degrees. So this plane flew around for a while because they noticed this, and they burned off some fuel. And the question is, what should we do? Should we land this plane? What should we do? I mean, there's nothing you can do while this thing is in the air. The nose landing gear was stuck. It didn't retract. It was stuck in this position. So then the pilot landed, and I'll show you what the landing actually looked like. So this is basically on this branch over here at 90 degrees. Okay, so you're not steering, right? So you're basically using the nose landing gear as just a braking mechanism, if you like. So let's run this video. It's quite amazing. So there's the touchdown, but the nose landing gear is still in the air. So they try to slow down, and there it's touching. Okay, I hope everybody could see this. This is really quite amazing. This is basically landing with a stuck nose landing gear at 90 degrees. And what I'm telling you here is, if the pilot would have had the opportunity to actually turn the landing gear a little bit out of the 90 degrees, he could have actually steered the aircraft a little bit. Now, to understand what's going on, I have to ask whether anybody's ever skied or seen skiing or skating, because if you're on ice skates, say, you go like this, and if you brake, you actually turn your skates 90 degrees, and that's how you, like in ice hockey, for example, that's how you can actually brake, because then, sort of like the nose landing gear being stuck. But ice hockey players, even while they're braking, they can still steer by wriggling around the 90 degrees. So they can go a bit to the right, they can go a bit to the left while they're braking. So this branch, which is really quite surprising, gets picked up by this aircraft model. And absolutely amazingly, there is actually an incident where this has happened. Okay, so now let me continue on. And so I showed you two examples, right? I showed you this example for 70 meters per second. I showed you this example for 90 meters per second. So this is a one-parameter bifurcation diagram where we plot the total speed of the aircraft as a function of the steering angle, okay, as we follow the circular solutions that you're getting. And some of them are unstable. In this case, a lot of them are unstable. Now you can do this for several different initial speeds of the aircraft, and then you get lots of curves and they sort of look different. And whenever the curve is red here, it's unstable, and whenever it's blue here, it's stable. And it's a bit hard to see what's going on. That's why it's very useful to make a three-dimensional surface out of it. So what are we showing here? So we have the total velocity here and the steering angle here, and now we're showing what we call Tmax. Okay, so this is the maximum speed at which we're starting to initiate the turn. And the two slices I've shown you is at 70 and at 90. So both are unstable. The C70 just went through this little red region here where the turning angle, the turning is not stable. And the C90 is quite more spectacular. And here over the side, you have this other branch. You have to be pretty fast in order to get this branch. If you're too slow, you don't have it. And so what's the engineering relevance of this plot? The plot, we can calculate these curves directly, generate the surface. And if you're an engineer or an aircraft designer, you want to definitely be below the red region. So never go land at more than, say, 60 meters per second and start steering. And of course, for safety, the normal turnoff goes at even slower speeds. So this is showing how the tools of following stable and unstable turning solutions, you do this in these different slices, you can get what we call a two-parameter bifurcation diagram. It now depends on the turning angle as well as the initial velocity can give you information how you might design or operate an aircraft. Okay, but now to the fun part. I would like to show you what it looks like when the aircraft is actually not performing a stable turn. And it does something that we call a relative equilibrium or relative periodic motion. So this is the picture I showed you before. If you fall off here and you land at 90 meters per second, you start steering. Once your steering angle reaches about 8 degrees, you fall down here and you get into this region. And you see these dots here. This is the maximum and minimum velocity that you get during the operation of the aircraft here. So it will no longer follow this dashed curve, which is the turning circle, you know, turning with a particular radius of a circle. This is not actually stable, and the aircraft will do something else. And I have a video to show you what this actually looks like. So, okay, I should have, I guess, magnified this, but this is actually quite handy now. So let me go. Oops, I'm going backwards here. Sorry. Stop. Okay, so here's my aircraft. I hope everybody can see the video. So the aircraft is at constant thrust. So it attempts to make a turning circle of a certain radius at a certain speed, or rather thrust setting. And if we let it go, you can see it sort of makes the turn, but then it badly spins out of control. And it comes to almost a complete stop because it went sort of backwards, but of course the engines are still pushing it in the forward direction. And then it keeps going. It starts basically at 0 velocity and becomes faster and faster. And it's doing a decent job at doing this turn. You can see the turning circle here. Okay. But then the way to think about it, that's why it's a relative periodic motion. And when you're here, you have to take this entire curve and glue this bit over here. So it would do this again and again and again. It's sort of like when you do, a spiral, you take a pen and you do this kind of stuff. Okay, so this will now repeat. So the motion of the aircraft relative to this curve is periodic, but it's not the same curve. Okay, and the curve is the curve that the center of gravity of the aircraft would follow. So let's watch this one more time. And you can see that the aircraft turns around a full circle relative to this curve. See? So it's now turning to the right. Okay, spinning out of control. Okay, and then it keeps going and it goes faster. It's attempting this turn again. Okay, and that's it. So this is what it looks like when you're going around the corner too fast. It's a bit like on a car or motorcycles, more dangerous, I suppose. But in a car, if you would do this on ice, you spin out, you would also do some sort of a turn relative to the curve that you're traveling in. And now we had an idea to apply this for practical purposes. And let me see if I can do this here. Okay, I would like to, oh yeah, here we go. Okay, so our idea was to have the terminal building over here, okay? And then you can see what the idea is. The aircraft comes, and here we go. It parks perfectly at the gate. So that would be sort of the Blues Brothers approach to parking an aircraft at the gate. I don't know if you've seen the movie Blues Brothers, but they have a very funny way of parking their car by sliding it into a parking spot. Okay, so now the aircraft comes to a stop. Everybody can get off, new passengers can get in, and once you have loaded, then you just drive off again. And it completely takes care of having these machines that push the aircraft forwards and backwards and all the rest of it. You may have already have an inkling that our sponsors were not too happy for safety reasons to actually operate an aircraft like this. But anyway, this is just a bit of a fun idea. You could, in principle, park an aircraft at the gate like this. Not to be recommended or to be tried at home. Right. So now let's go back to the talk here. Oh, excuse me. Here we go. All right. So that was fun, but actually we want to do some more serious stuff, and this is what we can do. We can now have a look. If you look at this picture, that we have divided this up into several regions, A, B, C, and D, where you find different kinds of properties of this particular term. So it doesn't always look exactly the same, and we can actually characterize this. For example, if you're in region A, I mean, the picture looks almost the same. You see, you have the aircraft, and that it doesn't quite come to a complete stop, and it doesn't have quite the cusp-like shape I showed you before. But you know, the aircraft then keeps going. But if you actually plot alpha, which is the angle the aircraft makes with respect to the curve, you can see that the aircraft starts sliding to the left, but then it catches itself. So the aircraft does not actually make a full turn with respect to the curve that it covers, that it is tracing out on the ground. So if you were on this aircraft as a passenger, you would feel that the back breaks out, but then it sort of comes back as you go around this not perfect circle. You see, you know, you have this really very sharp turn here, which you should not be having. So you're sliding out, but it's not so bad. However, if you enter region B, then you can see that this angle here, this is in degrees from 180 to minus 180, actually has a actual discontinuity here over 360 degrees, which simply means that the aircraft is now actually turning 360 degrees. So as you go around, the aircraft makes a full turn before it continues on. So this would be probably not a very good experience for passengers. Certainly, you should definitely be buckled up and not have a glass of wine in your hand. Okay, so you can see we can characterize the nature of the actual turn, and so to speak, how bad it is in this way. And why is this of interest? We can actually, and I've not shown the results here, we can then actually also figure out what is the actual load on the individual tires. So yes, you don't want to go around the corner with an aircraft like this, but even if you don't go around so extremely, from this modeling, we can tell you how much how much forces you have on the tire and how the tires wear out and all that kind of stuff. So you can do quite a detailed analysis of what's happening when you go around the corner, both in the stable regime as well as the unstable regime. But in order to really understand why the aircraft is sort of spinning out of control if you go around the corner too fast, this sim mechanics model is in some sense not good enough. It's a very big model. It's sort of black box. It is a single aircraft. You know, it's some aircraft that was modeled. It's not very flexible. So a project that we did with former PhD student James Rankin was actually to develop a completely parameterized aircraft model. So the idea is pretty much the same as the sim mechanics model, but now we do modeling from mathematical first principle. And on the left, you see these pictures. You see the aircraft from the side, from the top, from the front. The center of gravity is this point here. So you have a 3-degree of freedom rigid body. We're not assuming any bendiness of the aircraft at this point. We have the engines. There are some points. So the force is attached at the center of the engine somewhere. You can see the landing gear is fully parameterized where the landing gears are. Also the forces, how heavy the plane is. So this is a 6-degree of freedom rigid body model, fully parameterized. It works for any free post aircraft. We have a ground tire model and we have the aerodynamics. So in some sense, it does what the other model does, but it has lots and lots of parameters. For example, where is this landing gear? How far is the landing gear in this direction? How far is the landing gear in this direction? Here's the CG, and this is the turning point. So they are not the same. Where is the turning point? I mean, the way around which you turn the aircraft relative to the center of gravity. Where's the engine thrust applied? So these are now all parameters, and the idea is that this can model any aircraft you like, whether it exists or it doesn't. So this is really a design tool. If you are designing an aircraft and it's a 3-post aircraft, you just have to specify what all these parameters are, and then this model will model what your particular aircraft does. For example, you can now study not just dependence on the steering angle, which is this delta here, but you can also say, okay, what happens if I move the landing gear further to the back or further to the front, or make my aircraft bigger, or put the engines in a different position. So it allows you to check and sort of have a rubber aircraft, if you like, where at least mathematically you can move things around and check for its ground maneuverability properties and basically optimize it, or at least test whether your aircraft goes around the corner at desired speeds and is safe and doesn't spin out of control and so forth. Another important parameter are these forces in newtons. And for example, you can study the same aircraft, whether it's heavily loaded, lightly loaded. Is the load more towards the front or more towards the back? And I mean, these are also very practical questions that people can study. Now that's all good. We can do sort of the same thing. And now what we have actually done is we have asked ourselves, what is the nature of these strange periodic orbits that I showed you? Okay, so this periodic solution relative to the ground trace. And here is now this point H1 and H2 I alluded to earlier. So these are called Hopf bifurcations. And in the Hopf bifurcation, you actually generate a stable solution. So it's basically the undamping of some sort of oscillation. And in this case, it is the aircraft is no longer following the ground trace stably as a curve on the ground, but has a motion relative to the ground trace. Again, on the bottom right, you see another example of this. You can see the aircraft attitude changes. So a stable turn would mean that the angle the aircraft makes with the ground trace is constant. This is what you get when you go around a circle, right? You have always the same angle of the aircraft relative to the circle as you go around. So that would be a relative equilibrium, and now we have a relative periodic motion or oscillation. So the interesting thing here is that we're now plotting actually the forward velocity, Vx. Before I showed you the total velocity, modulus of V, but here I show you the forward velocity. And the forward velocity has a maximum. Okay, so what we're showing is the maximum and the minimum of the forward velocity. So the forward velocity is pretty much the same as you would have if you were doing this turn. Okay, and this happens along the part, let's say over here, where you're more or less following the turn very well before you start spinning out of control. But when you spin out of control, you can see that you also have a very low forward velocity. In fact, you can see the zero line is over here. And so you have a negative forward velocity, which means that the aircraft spun around 180 degrees and it's now going backwards along part of the circle. And that's what I showed you in the video. And this is also another example of a very similar kind of motion. And from the practical and mathematical point of view, you can see that if you, let's say, you have a steering angle over here at a certain velocity and you decrease the steering angle, it can become unstable. And you can see, first of all, it's sort of a small oscillation, but then very suddenly, the forward velocity drops dramatically below zero. So this steep drop corresponds to suddenly the aircraft really spinning around and going backwards part of the way. And you can see on this side, at this Hopf bifurcation, this happens very rapidly. So basically, as soon as you have this instability, you have this massive drop in the minimum of the forward velocity, and it immediately gets negative. So basically, you spin out of control really very quickly. Now, the interesting thing is that we can do some cool mathematics here, and we can plot the forward velocity in x. So x is the forward direction, and y is the sideways velocity. Okay, so I mean the velocity is a vector. The z direction you don't have to worry about because we're on the ground. So really just the forward and the sideward motion of the aircraft matter here. And you can see you get this periodic solution if you just plot the forward and the sideways motion. So let's have a look what's going on. You start here and you're nicely making your turn. Your forward velocity is increasing because the thrust drives you faster and faster along the circle. This is sort of this part here, okay? And then while the sideways velocity is practically constant and almost zero, as you can see, it's practically zero. But then something happens and you go around the corner, and then you make this excursion, which corresponds to the spin here, and you're going backwards. Now, then the importance of these dots that you see here is that these dots are at equal time distances, right? So this whole thing has some period, and every dot is a certain fraction of the period. So if the dots are very close together, that means that this is a slow thing. So oops, I'm sorry. You go around this quite slowly. And then you go here, and then something happens, and you do this very quickly. And you can see this. You can see this in the movie and also in this thing. As soon as it spirals out, the spinning out goes very quickly. The aircraft goes backwards, effectively comes to a stop, and you can see that here. Okay, the forward velocity goes to zero after it was going backwards because of the thrust. And then you have another go at making a turn. So this is also what we call slow fast dynamics, and this can be described by mathematically quite nicely. I'll come to this in a second. But the observation is that Vx acts as a slow variable and Vy acts as a fast variable, and all these other variables, I will not go into the detail here. All these other variables, even though it's a 6 degree of freedom system and you have 6 variables, okay, you have x, y, z is up, and then you have the angles in each of these directions. This is a 6 degree of freedom rigid body model. What really matters here is only the forward velocity and the sideways velocity, and they act as slow fast things. So if we represent this in the Vx, Vy plane, as I just done, there is no observable dependence on actually the steering angle. And here's the picture, and this is maybe a little bit mathematical, but this is called the Canard phenomenon. So this is where the Hopf bifurcation is. You get a very small periodic solution, which grows very rapidly into this big one, and this big one is effectively the representation I showed you before. This is what's happening near H1 on the left, and this is what's happening near H2 on the left. So this last big circle is what I showed you the video of, effectively. And the key thing is that the mathematical theory tells you that you go from the small onset oscillations, let's say over here, very quickly to this spinning out, which is a slow fast phenomenon. And so the way to think about it is that the aircraft starts to wiggle a little bit, but then very quickly it spins out. And I will summarize this in a moment, but I would like to compare the two vehicles. I told you it's a trike. So if you want to compare what a trike design aircraft or 3-post aircraft does to an actual trike as a children's toy, I have to tell you that they are really not the same. Okay, there are big differences, and I don't have the time to take audience suggestions of what's different between these vehicles. So let me tell you. First of all, there's a difference in how many pilots you need. You don't need a license for the vehicle on the left, but you definitely need a pilot license, even on the ground. You have no passengers, and you have many passengers on the right, and there's no onboard service if you're going to drive your own trike, and you usually only get coffee, tea, and water on aircraft. But joking aside, the key thing is the whole analysis I showed you shows that if you have a trike configuration, because the center of gravity is much higher, the trike will actually topple over. So in principle, all the dynamics I showed you, you could also do on the trike on the left, but you cannot do it if you do it sort of on normal ground. Maybe on ice, you can start spinning out with it. Okay, so an aircraft, even though it also has a trike configuration, because where the engines are and how it's set out, it is a much more stable thing in terms of the toppling effect. So aircraft don't really ever topple. So for example, you might think if this thing goes around the corner too fast and starts toppling, then the engine will probably hit the ground because it's only about a meter up from the floor or from the ground. This is actually not happening. I mean, you will not be able to topple the aircraft so that the engine hits the ground if you go around the corner too fast. It will spin out of control in the way I showed you. So let me wrap up here. So I showed you constant radius turning for an industry tested aircraft model, and the loss of stability is due to the onset of oscillations. But really, this phenomenon, which we call the Canard phenomenon or Canard explosion, which is a pretty dramatic term, it's only a mathematical term, rest assured, it's giving you this stability boundary. So what really is happening physically, when you go around too fast, you have two tires, right? You have a tire on the outside, you have a tire on the inside. Even in the car, you will know that you will tilt a little bit to the outside because of centrifugal forces. So you have more force on the outside wheel than on the inside wheel. But both wheels are actually required to hold you in place and complete the turn and be stable in the turn. And so what happens after this hop bifurcation is that the wheel and the inside starts slipping a bit. So it slips. So you start to wiggle out, but the wheel on the right, on the left, on the outside, in my case here, on the outside wheel, is still able to hold the aircraft. So it stabilizes the aircraft. It doesn't really spin out of control. And then the other wheel catches again, and you sort of just wiggle back and forth a little bit, sort of like a bee in a wiggle dance. However, very quickly afterwards, when you saturate the first tire, so the first tire starts slipping, the outside tire has a bit more force on it, so it's not quite slipping. But if you go ever so slightly faster, then the outside tire will also slip, and then there's nothing holding the aircraft, and you start spinning. That's basically the physics of what's behind what mathematically is called the Canard explosion. We actually have a 2D model for this type of Canard explosion, which is not the standard one in the mathematical literature. But in any case, I will not give you these kinds of details here. If you're interested, the papers are available if you want to have a more detailed look. So anyway, future work would be really cool to have test data. So somebody give us an aircraft and we're able to spin it around in the way I showed you. Of course, that's never really going to happen. But the key thing is to detect directly the stability loss, understand what the stability loss is, where it is, so that you can actually avoid it in actual operation of actual aircraft. And again, one big driver is that you want to control ground maneuvering. So you want the computer to also drive the aircraft on the ground. And if you want to write any control system for anything like this, you have to have a very, very firm grasp of the stability properties of the system and the mathematics and the description. So because otherwise you cannot control the thing. If your controller doesn't know where the dangerous boundaries are, then you can't really design a good controller. And with this, I would like to finish and hope that you will enjoy your next flight. I should stress from my sponsors that flying is still an extremely safe mode of transport, and especially if you're still on the ground. Thanks very much for your attention.
Thank you, Professor, for that insightful talk. So now we move on to the Q&A session. So the audience can ask questions from the speaker. So either you can use the chat box or you can simply unmute your microphone and ask a question.
Okay, I'm happy to take questions either by yourself unmuting yourself or typing it into the chat, whatever you're more comfortable with.
Okay, sir. I have a question, but first of all, thank you for the very interesting session. I hope I am audible and clear. So in like one of our undergraduate courses where we are given an introduction to nonlinear systems,
Yes.
the way we analyze, so for example, if we are creating bifurcation diagrams, we use the introductory methods like system linearization. And
Yes.
for hop bifurcation, we use like analysis of the eigenvalues. So
Yeah.
what sort of techniques do you use in these complicated systems? Is it similar, or do you use more advanced computational methods and such? So
Yes, I will maybe go back to an earlier picture. Okay, maybe like this. So, okay, let me go to this one, okay? So here you see the stability of the branch. Okay, so what we do is we follow the branch with what's called continuation methods. And while you're following the solution, you're indeed checking the eigenvalue spectrum. Okay, so this is a 6-degree of freedom system. You have 6 eigenvalues. And when you, for example, you come this way and you detect this point, you detect a Hopf bifurcation. This is done with advanced numerical techniques. So the equations are so complicated that, you, of course, in principle, you could calculate the, this relative equilibrium and calculate when you have a Hopf bifurcation, but it's just not particularly practical. But there's good software that does it basically just as good as you would to do it by hand. So we follow this branch, we detect it becomes unstable. We follow the unstable branch, we detect it becomes stable again. We got the 2 Hopf bifurcations. So that is effectively just what you mentioned. Okay, you do a linear stability analysis. But then, of course, if you want to know what this periodic solution here does, a linear stability analysis is no longer enough, because it will not tell you what the periodic solution is. It will only tell you that you should expect to have some periodic solution nearby. And for that, we also use continuation methods, which allow you to switch from this point and follow this periodic solution and follow it in parameters. So this curve you see, this is a continuous curve. This has been followed from here. Okay, so I mean, it's a periodic solution. You have a maximum and a minimum, right? This is the minimum and the maximum along the solution of this variable Vx. And we can just follow it, and then we can see it goes back to Hopf bifurcation. So we have a periodic solution in between these 2 Hopf bifurcations. And we know what the periodic solution looks like. It looks like this in this projection, and it looks like this if you plot it relative to the ground trace of the aircraft. Okay, so in basically the techniques that you're learning in your courses are super relevant for this, in combination with clever ways of implementing this in a computer and slightly more advanced things. I hope this answers your question somewhat.
Yes, sir. Thank you.
Okay, we have another question in the chat. So the question is, why not try to steer all wheels during the ground maneuvers?
Sorry, can you repeat the question? Okay, I can look in this chat, of course.
Why not?
Why not try to steer always? Ah, okay. Yes, okay, there are very easy reasons for this. It's very expensive to steer anything, right? The aircraft is supposed to be on the ground. Now, if you're a flight engineer, you actually don't want any wheels whatsoever, because the wheels are just in the way. You will know that the wheels have to retract really quickly, so they're not in the way. Actually, any of the wheels and anything on the aircraft that you need on the ground is just dead weight once you're in the air. So that's why the landing gear should be as light as possible, as little wheels, as few wheels as possible. And steering the back wheels is not going to give you any tangible advantage. You may know that even in a car, you're only steering the front wheels. You could say, why am I not steering the front wheels in a car? Sorry, the back wheels in a car. If you have a super fancy car, a very expensive car, the back wheels will actually steer a little bit, just a few degrees if you go around tight corners, because then you can make closer turning circles, right? So it helps you maneuver into and out of parking spots. But if you go above a certain speed, even the very fancy cars don't steer in the back. The other thing is that steering in the back is a very difficult thing. And I can explain this very easily. So you're in a car and you go forwards. You steer, it's inherently a stable thing. If you let go of your steering wheel, okay, I mean, I'm not suggesting you actually do this, only if you have a lot of space, the steering wheel will self-right and you will keep going straight. So the going straight solution when you steer at the front is stable. But it's not true if you steer in the back. And you can try this out yourself again too. But again, don't try this at home. Be careful of safety and stuff. Don't say Bernd said, you should drive the car backwards. But, every now and then, you go backwards in a car to park, for example. If you were to drive a car at reasonable speeds, let's say 50 kilometers an hour, you can steering at the front. It's stable. We all know it. We can do it. But you would not be able to drive a car backwards at 50 kilometers an hour. Because as soon as you steer, you would spin out of control. Steering backwards is actually an unstable way of steering. It has the advantage that it increases, how fast you can steer, but it is inherently an unstable way of doing it. So that's why it's much more stable to go forward than backward with a car. I hope that answers this question somewhat.
Thank you, Professor.
I think there's another. Yep.
Sorry, Ben, can I ask a question?
Yes, of course.
Yeah. So now if I'm going to go with the picture in the screen. Now, if you think about the Hoff happening at the first Hoff bifurcation, H1, right? Now, normally, if you like consider Hoff bifurcation, like the periodic solution, like gradually like increase like the maximum, like the minimum values of the periodic orbit. But looking at that H1, like if you look at the Vx component, like soon after the periodic orbit as Bernd at the Hoff bifurcation, that the Vx, like even without moving delta a bit, like the minimum value of Vx has been increased a lot, right? So the question I have is like, while you continue this periodic orbit using the numerical continuation software you have, did you face some sort of a numerical challenges to detect it and continue in the parameter?
The short answer is no. So first of all, of course, on this scale, you don't really see what's going on. So if I were to sketch this, okay, so here's my Hopf bifurcation. Excuse my sketching skills. This is only with my mouse here. Right. So if you were to really look, it would look like this.
All right.
Okay. So a little bit like on the left, but on a much smaller scale. All right. So it's the software. I mean, this is done with Auto for this model. Auto is actually good enough to do the branch switching, but it is, of course, a numerical issue that the periodic solution gets very large, very fast. So in this case, you can see on the right here, it's actually easier, right? Initially, it's nice. It's a square root-like as you expect near a Hopf bifurcation. And so that's no problem. And then suddenly it becomes much larger. And if you were not to use continuation methods based on boundary value problems, then it would be very difficult to you would not see this jump. And in fact, let me go back to an earlier picture where we use the sim mechanics model. Look, this is the same picture, but here we only have dots, okay? Because we could only use simulation. We could not actually continue periodic solutions. We could continue the relative equilibria with the sim mechanics model, but not the periodic solutions. And you can see we sort of resolve it on this side, but on this side, there's no way you resolve it. So it's a subtle thing, but that's why we actually developed the other model, because then we have actual equations for the whole thing, and we can also follow the periodic solutions and resolve this, even when it is extremely fast. And the reason is that we are, computing step size in the product space of parameter and solution. I have shown you this picture. So these solutions, they change a lot, but this all happens along this vertical line. But because with the step size is determined also by the size of the solution, the continuation of the periodic orbit is actually able to resolve this. I hope this was not too technical for a lot of the other listeners, but basically the technology or techniques that we're using are able to deal with these kinds of slow, fast things, even if it sounds reasonably extreme. Okay, there's more question in the chat. Okay, let's see. Add an extra wheel. Okay. Yeah, okay, so why don't we add an extra wheel? So there are aircraft that have a lot of extra wheels, like, 747, A380 actually has 4 posts, but it's all to take the weight. Even the biggest plane, they only steer with the nose landing gear. And why is a car more stable? Because it's square, right? Okay, it's much more stable to have a wheel here and a wheel here as you go around the corner. But, how are you going to attach this to an aircraft? Okay, you really don't want to have a hammerhead kind of nose. That would not be very good from an aerodynamics perspective. We should never forget that planes are really designed to fly, and so they make the best of that. And the trike configuration with only the nose gear steered is basically the way to go. If you're building a ground vehicle, don't build it like an aircraft. Okay, that's basically the punchline. Okay, thanks, engineer. Okay, wheel we're placing closer to the engines. Yes, bearing the height. Yes. So this has all been investigated. So where you place the wheels depends, of course, on the weight distribution of the aircraft, where the engines are, and so forth. And that's actually the usefulness of a model like this one, where you are actually able to play around with these parameters. Okay, you can test your aircraft. You go around the corner, and maybe it's a bit unstable or it spins too fast. Move the wheels further out. In principle, in a trike, if the wheels are further out, that's better. But of course, the issue is also that then the wings have to take the full weight of the aircraft, right? For example, there are some aircraft where the smaller type aircraft, they have a tri-configuration and the wheels are actually attached to the main fuselage, not to the wings. They actually have to strengthen the wings quite a lot to have the main gear attached to the wings because it has to take all the weight when you're landing, okay? And of course, I mean, on the ground too, but sometimes you have a heavy landing and it has to take more than just the weight of the aircraft when you have a heavy landing. So the oleos is also a good one. You don't want to have too much oleo, too much compression, because you have to maintain the distance of the engines from the ground, for example. So there are also limits of what you can do there. You don't want them to be too soft because then you wiggle around corners. You may know that some older cars with soft springs, they are not so comfortable going around corners. So sports cars tend to have stiffer springs because then you can corner better. But of course, that takes away passenger comfort, right? You could, in principle, have a landing gear with basically no shock dampers, but that would be a very rough ride. So these are all these kinds of compromises that people have to make when they design, where to place the wheels on a commercial airliner. So again, if you're into ground vehicle design and you optimize all kinds of things, the vehicle that you would be designing would be very unlikely to look like an aircraft in the end. On the other hand, people are also interested in flying cars these days. Okay, so they make all kinds of other funny constructions. So having something that can both fly and drive around on the ground reasonably stably is a tricky proposition, as you may realize. Are there any other questions?
Yes, but it's a more general one, because there are students who are maybe interested in focusing on mathematical modeling perspective. You are dealing with the 6 degree of freedom system where you have to deal with 6 variables, right? So I'm asking now at the beginning when you started the research, there was this semi-mechanic model, right? So moving from that one into this fully parametric model of 6 variables, how difficult it was to develop that model with 6 variables, especially starting with deciding this is a 6 degree of freedom model, right? So likewise, so can you take us through a little bit along the journey of where you have developed the model?
So when we started the project, the sim mechanics model was there. It was a specific aircraft, A320 basically, okay, and you can work with it. The disadvantage is that you can only do limited things with it. First of all, coupling it to continuation software was a non-trivial thing because it was not designed to be used in this way. Normal models in industrial context are generally designed to be used as simulation tools. Okay, so you can run and see what it does, and if you want to change something, you use another initial condition, or you change a parameter, you run it again, you run it again, you run it again, you run it again. So it's a very tedious process. It's time-consuming. It costs a lot of computer time. So these continuation methods are much more efficient if you want to find out what the stability boundaries are, for example, as you very well know, and that anybody who takes the course in dynamical systems or ODEs understands this. But these models were never designed like this, okay? So we managed to couple it to the continuation software, which was, Etienne Coetzee did this, and this took about a half a year. So it's a non-trivial exercise because it has all these boxes and, it has if-then-else statements in there, so you don't even know if the right-hand side is smooth. I mean, all kinds of trouble. Okay, and then we said, okay, this is good. We got good results, right? We got basically even the periodic solution. It's not bad. If you think that this is not done by continuation, it's actually not bad, right? We were quite happy with it. But if you really want to see what's going on, you have to go to the trouble and develop this model. So now to answer your question, James Rankin put this together. It's a non-trivial exercise. You know in principle how to do it. You have Newton's laws and all the rest of it. You have to parameterize everything. You just have to be very careful. It's about force balance and so forth. You have to have a tire model. The tire model, we used an established tire model, so we didn't really model the tire here. There are tire models that you can use. And so basically, it is a big bookkeeping exercise to make sure the whole thing works. Then you need to test it and make sure that if you take the same parameters that, for example, represent an A320, you get the same results that you're getting with the sim mechanics model, okay? So you can always, the problem is you want to have an industry validated model. Anybody can make a model, but you don't really know whether it's correct or not. But we were lucky, we could compare it with the industry tested models, okay? So that whole process of writing down the equations, checking them. I mean, in principle, it's not a hard exercise. There's a very systematic way of going about it. You take your rigid body, then you have interactions with the ground, you have the forces, you have the center of gravity, okay? So it's just a lot of parameters in there and some reasonably long equations. You can't make a plus minus sign. You have to be really careful, but you need to be able to compare it to something which you know is correct. That's actually the biggest problem in this kind of modeling. And we were lucky to do this. And in fact, this took also about a half a year. I mean, model development, writing down the equation is one thing, but making sure that it actually checks out is what takes the time. It's like when you write a program, writing the program is sort of fast, but debugging it and making sure it actually works, that's where the time investment is. So it's not dissimilar to writing a reasonably complicated program, right? You know how to do it in principle. You have to go about it quite systematically. At every step, check all kinds of things, and ideally be able to check it against something that's verified. So you have sort of a ground truth that you can compare it to. I hope that answers your question a little bit. But it takes about a half a year for a pretty good student. So it's a major undertaking. You don't do it lightly. You don't just okay, Saturday afternoon, what am I going to do? I write down an aircraft model. I mean, this would be a lot of work. Any more questions? I'll see if anybody types in the chat.
So I have a question
Yep.
about the fighting aircraft. So I have heard that in fighting aircraft, there is an unstable mode of operation. I mean, there is a pole in the right half plane. Like
Are you talking about fighter aircraft?
Yeah. So the number 707 is also coming from 1 over root 2. I have heard that. Because
yes. Okay. So we had some. My colleague Mark Lowenberg has worked a lot on different kinds of aircraft types. I mean, he would be much more knowledgeable about this. But the short answer is that what you have heard is correct. I mean, first of all, fighter aircraft are not very concerned about ground maneuvers either. Okay, so they on the ground they're not too dissimilar. I mean, the weight distribution is different, but everything I talked about here, this model could in principle be adjusted for a fighter aircraft on the ground. Okay, but more interesting is the maneuverability in the air. Okay, and as I mentioned, if you drive a car backwards, it's much more maneuverable. If you drive 100 kilometers an hour and you want to suddenly go to the right, you can do this in a car, but it's not as quick. If you were to go 100 kilometers an hour in a car backwards, you could change direction very quickly. Now the problem is, as I mentioned, this is inherently unstable. So as a human, you will not be able to go 100 kilometers an hour. Even if you cling to your steering wheel, a slight deviation will start spinning you out of control, okay? So what you need a control system that if you go backwards in a car at these speeds, that keeps you on the straight path, or any other maneuver that you want to do, okay? So modern or latest generation military aircraft tend to indeed be unstable. So for example, if you take an A320 and all avionics go out, but you still have control over the surface, you still can control the aircraft, but the flight control is off, that thing can still fly sort of on its own passively. Okay? It's like a glider. You can still fly this thing, even without engines. Okay, if the engines go out, lots of stuff go out. If you still have the control surfaces, whether with wire or hydraulics or whatever, you can still fly it. With these modern aircraft, they are flown in unstable modes. You're absolutely right. So if the control system fails, you will basically it would spin out of control without the control system. Okay. And why do they do this? The computer power is better. The control systems are good. They have something like around 40,000 control inputs every second in order to keep this thing not spinning out of control. So you can imagine a human is not capable of generating 40,000 control inputs per second. It can only be done by computer. And you have to trust your computer if you're the pilot. If that thing doesn't work anymore, then you basically have to abandon your aircraft. I think that answers your question. But the comparison with the car going backwards is a good one in this case. Right? So they do it because it increases maneuverability, but it makes it inherently unstable. And it always sounded like a crazy idea. Nobody's ever done it, but now with computers, you can do it.
Thank you, sir. Do we have any other questions? Okay, I don't see any other questions. So I would like to convey my heartfelt thank you to Professor Krauskopf for sharing your time, knowledge, and passion with us today. So your insights into the mathematics of high-speed aircraft maneuvers were truly fascinating, and we deeply appreciate the clarity and enthusiasm which you presented. And again, a big thank you as well for all the participants for being part of this session. So we hope you that you find this talk inspiring and insightful. So once again, I would like to thank Professor Krauskopf. We are truly grateful for this wonderful talk. So with that, we are going to conclude the session. Wishing you all a great day.
Thank you very much, and again for showing up on the Saturday. And I wish you all a good weekend. Bye bye.
Thank you, Bernd. Bye.
Thank you.